Okay, I think we're perfectly on time. Last people are joining in Zurich. Feel free to start.
Okay. Welcome everybody to this Liip talk. Today I want to talk about concurrency control in databases. I split the presentation into parts. First I want to give a short introduction to all these treatments and methods and the theory behind it. As this can be a rather hard to explain topic and can be dry, I want to focus on the second part of the presentation on concrete implementation details using doctrine. So, as you probably know, a transaction is the unit of work in a database that follows the exit terms. Message stands for consistency, isolation, and durability. And transaction are used to move several queries into a logical loop that where either all statements succeed or none. So this ensures data consistency, which is the C part and method. But concurrency usually is about the isolation part of asset. So isolation means that transactions that cannot interfere with each other. This task to apply operation constraints into the system, and that typically will result in some performance degradation. And concurrent operation means that overlapping in time, not serially. There are two categories of concurrency control mechanisms. One is pessimistic and the other is optimistic. And pessimistic means that any operation of a transaction that might violate the asset rules or other business rules will block other operations until this operation is finished. So for that, it uses locks. So if you have two transactions that both try to modify a row, then one will block until the other is finished. And this is used with locks, and as you can imagine, locks limit the effective concurrency. So basically means two transactions are then executed serially instead of concurrently, even when they were started concurrently. And the other approach is optimistic. Optimistic assumes that multiple transactions can frequently complete without interfering with each other. And that is usually used in workloads where you usually read more than you write, because you don't want all your select statements and stuff block other users. They only should block when there's a conflict. And with this approach, you achieve higher throughput than with other concurrency control methods. To implement optimistic concurrency, it involves 4 phases. First, you record a timestamp at the transaction beginning. And later, when you modify the data, you read the values again and compare, then validate if the version you had at the beginning of the transaction is still the same as the version when you try to modify the data. And if there's a conflict, then you typically abort the transaction. And if there's no conflict, then the changes can take effect. And there are also other conflict resolution mechanisms. It's not only aborting, but also merging data and stuff like that. It depends on the business logic you want to achieve. But we get to that as an example later. So how do databases actually provide concurrency control? Most of databases implement so-called multi-version concurrency control. For example, MySQL and PostgreSQL. What it does is that each user connected to the database actually sees a snapshot of the data at this particular point in time. So when you have two transactions reading values from the database, both transactions actually see the data as they were at this moment. Yeah, as you can see, that it provides isolation because one transaction only works with a snapshot of the data and not with the current data. When updating an item, it will not overwrite the old data, but instead marks the old data and move it somewhere else. But you can see this is basically something similar to Git. Like in Git, you also work on specific versions, but it's explicit. You always work on a commit hash, which is a version identifier. But in database terms, it's usually the transaction boundary, which makes a snapshot, and that's a version. And the main advantage of it is that reads never block, because reads can always just work on the copy of the data and don't have to wait on other things. Database also provide a so-called transaction isolation level. This means that it allows to adjust the strictness of transaction isolation. So basically, you can adjust how strict your isolation is you actually want to have for this transaction. So there are 4 different levels: serializable, repeatable reads, read committed, and read uncommitted. And serializable is highest, and read uncommitted is the lowest level. The higher the level, the more you can decrease so-called concurrency effects. Concurrency effects are, for example, dirty reads and lost updates. So dirty reads would be you read something in your current transaction that has not been committed in another transaction. So it might actually not be real data, and that's not what you really want. Yeah, and the higher level decreases these effects, but on the other hand, of course, reduce concurrency and increase the possibility of deadlocks. And if you then you increase the rate of transaction, so higher throughput. But on the other hand, you have to carefully construct your transaction to not cause software bugs, which, for example, are race conditions. So, yeah, it's a developer's task to either choose the correct isolation level or to write correct transactions. And the difficult part is also that the default isolation level changes between database management systems. So in MySQL, for example, the default is repeatable read. But I don't go into concrete detail what that means. Maybe you can ask that later. Yeah, let's get our hands dirty. From my experience, when you start developing database applications, you usually neglect concurrency at the first moment. And you only realize that when you do load tests, for example. Because the standard use case is not that concurrent. So it would only happen if one user opens many requests at the same time, many tabs. This is rather unlikely. So usually you see it when you do load tests with many requests at the same time. Yeah, and it's a developer's task to implement concurrency control on a case-by-case basis. And it's also hard to test because it would require functional tests that are executed in parallel and that actually overlap in time. So it's a timing issue. Yeah. So let's get an example. This one is just use case as you want to insert a row when the entity doesn't exist, or you want to update an entity if it exists. So insert or update, which is pretty basic. So the most standard approach and most straightforward would be like this one. In this case, it's a like, which is identified by user ID and an item ID, so like a Facebook like. And that's the primary key. So we fetch a like, and if it doesn't exist, then we create a like in line 3, and then persist it in line 4. And if it exists, we just update it, for example, the timestamp. And then we flush to actually make the queries. So in flush, Doctrine actually makes the queries and puts them to the database. So does anybody see what could go wrong with this implementation?
A like could be added between the find and the persist by something else.
Yeah, exactly. So
actually, even if it's added after, it's just before the flush.
Before the flush, yes. So the time between 1 and 8, basically, line 1 and 8, there could be another request that does actually the same thing. So both try to find the like, both don't find it, and both try to insert the like with the same ID. And then in flush, of course, we get an error because it tries to insert the same ID twice. So we get a duplicate key error. So one request would succeed and the other would fail out. And yeah,
we also have the scenario that something could unlike, and you're trying to update something that doesn't exist anymore. And so, well, you might want the like that to be recreated for updating nothing. And so,
yeah.
Can you repeat it for
Lucas said that it could also be the case that the like has been deleted between find and update timestamp, or between flush and update timestamp. And that means that it actually wouldn't update the row because it wouldn't exist anymore. So let's have a look at a full-featured solution, which also shows some other things. This is part of our micro API project where we actually have a like API. And this is just a controller that on a put request creates a like. How do I do that? New.
Use the AG. I think it's on the view, right? Yeah. You go to the view and then back to that.
Okay. So what we do here is at first we, as before, we try to find this like by these identifiers. And if it is new, so if it doesn't exist, then we create the like, and then the complicated magic happens. Let's start from inside to outside. So here we actually have also other business logic involved, like we have updates user last action, and we increase like count, which is the aggregation version of the likes for per user, for example. And we, of course, want to wrap that in a transaction because we don't want to increase the like count if the like doesn't get inserted, for example, or the other way around. So we have to create a transaction, and with Doctrine we can do it this way, which wraps this code in a transaction. Because by default, Doctrine only queues all changes of entities in a transaction that are done on entities, and then flush it. So if you insert many likes and then flush, all these likes you inserted are part of the transaction and flush. But this one, for example, executes another SQL statement, which would cause, if you don't use explicit transaction demarcation, would cause a new transaction to be created, which you don't want. So we use a transaction here. And then we wrap this again in an exception try catch block because we want to retry it a moment later. The problem with Doctrine is when a transaction fails on an entity manager, then the entity manager is closed. So you can't use it anymore to insert new entities or persist or whatever. So in this case, when an exception occurs, we have to recreate the entity manager, and we can do that with this line of code. And yeah, so, and then we wrap this old code again in a retry wrapper. Because, as I said earlier, whenever you use transactions, there's always a chance that deadlocks occur or that lock wait timeouts occur. So you can carefully craft your operations to reduce the likeliness of deadlocks, but you basically can never avoid it. There's always a chance that it happens. And if you want to ensure that it doesn't fail in this case, for example, the like gets ignored, so request is ignored and the like doesn't get created, we have to retry it in this case. And this is what the retry wrapper does. It executes this code 3 times if one version doesn't succeed. So when an exception occurs, it retries this code again. There's a short timeout in between. This retry wrapper is a callable, so we actually have to call that again then. And then the actually part that we want to solve in the previous example is that we have to catch the unique error exception. Because even if you have a transaction, it doesn't ensure that we don't create 2 likes at the same time. It just ensures that the logic inside is consistent, but not the 2 transactions that are separate from each other. So we just catch this exception, which is duplicate key exception, and then we can ignore it, because in our terms, if 2 likes are created, 2 same likes are created, the second like, we don't care about the second like, it's already there. So we can say new false and then return the appropriate response header, either 2 or 1 for created or 200 for it already exists. So, yeah.
Why is not the? I just one question: what the select? Shouldn't that be in the transaction as well, or at least in MySQL, there's select for update, where you say I select thing and then log this so others don't.
Yeah, exactly. It's just one way to solve it, and you always have to. So the question was if we can also select for update and use other approaches, and yes, we can do that. You just have to think about what is most performant. And in this case, we could also wrap this select in the transaction and make it blocking, but that would decrease the performance likelihood because you have actually would be pessimistic. This is an optimistic approach, right? And the other one would be pessimistic. We could also use other mechanisms like MySQL insert on duplicate key update in this case, but Doctrine unfortunately doesn't provide a database abstraction for that. So if you use insert on duplicate key update, for example, then you would be tied to MySQL and it wouldn't work on Oracle or Postgres. Or you could insert ignore, but that would also have other side effects. Yeah, just one solution. Shall we get it all done? You too. No. Okay. So yeah, I showed how to use implicit versus explicit transaction demarcation, how to handle exception and closed entity managers, and how to handle deadlocks, lock wait timeouts, and retry transactions. Now let's get to optimistic concurrency control. The stateless nature of HTTP makes it usually impossible to use pessimistic concurrency control for web user interfaces, because you don't want to lock if the user sees a form to edit something, and you can't just lock this row from concurrent operations because the user might not actually submit the form, or it takes endless time for him to complete it. So in this case, we use optimistic concurrency control. Let's look at the doctrine example. As I explained earlier, the optimistic concurrency control always involves we have to carry along a version identifier. So in this case, we add a version to our things we want to edit and make optimistic concurrent. And then you have to remember to actually carry that version along. So when you display a form, you basically have to put that identifier in a hidden field. So when the user submits the form, you can then check later with this code, for example, if that expected version is actually the current version. And if it doesn't, then Doctrine shows an optimistic log exception, and we know it has been modified by another user in the meantime. And then we can, for example, display the form again and tell the user he has to resolve the conflict. So, but that's a manual approach. Yeah, that's basically it for optimistic concurrency control.
Does Symfony handle that in the form bundle? So you don't have to add the version thing yourself?
Nope. I'm not aware of that. But there might be an extension or bundle for that, I don't know. Now we have an example for pessimistic concurrency control. As I said, pessimistic is used for doing locking reads. There are two modes available. It's pessimistic write and pessimistic read. Pessimistic write prevents any concurrent read and write operations. And pessimistic read only prevents concurrent write operations. Pessimistic write maps to MySQL or to SQL and select for update. And pessimistic read maps to select, log, and share mode. And let's get an example. What is kind of obvious is that we have to use explicit transaction demarcation, because in auto commit mode, only the select would be part of the transaction, and that wouldn't do anything, because we want to actually log the select for then to later update it. That's a locking read. This code is part of also Amigo API, where we process payments. And we start the transaction line 1, then do our query for all payments that have not been transferred yet, where the transfer relation is null. And then the most important part is in line 10, where we tell Doctrine that this query should be a pessimistic write operation. And then we can execute the query and process the payments and set the transfer relation, for example, and then flush and commit. So the standard transaction. Why we do that is because we don't want, if this command, which is part of command, gets executed at the same time twice, then the same payment could be actually processed twice. Because both would see, the payment has not been processed, so we process it and send and process it twice. And with locking, we prevent all concurrent operations that this select statement fetched to block until this operation is finished. Yeah, so as you might have seen, there is no one-size-fits-all solution. And usually developers have to think about it and try to find an implementation that is, first of all, fast and actually solves the problem. Because in theory, you could always just use, for example, the serializable isolation level, which would mean that all transactions are executed serially instead of parallel, but that would hurt performance very much. So you have to adjust things with isolation level and with your transaction writing. It's easily to do wrong. And if it's done wrong, then it either it doesn't achieve its goal to ensure correct results for concurrent operations, or it creates deadlocks, avoidable deadlocks that fail the transaction, and you have to retry transaction more, which also means that it gets slower. Or you slow down the request unnecessarily, for example, with a serializable isolation level. Yeah, that's it. Thanks for your attention. Do you have questions?
Yeah, thank you. Just a question. I saw in Google Docs they use something like operational transform, I think it's called, where they send the changes to at a specific time. So you type a letter and then it sends at whatever. If you type E, then it sends E to the server, and that there are concurrent users editing the same document and they merge it together. And I know that in JavaScript there's shared.js, but I wonder if there's something like that in PHP, or if, I don't know, across that while doing that.
I don't know of any library or something that solves concurrency problems automatically. So
you can still fail, of course, but it's merging thing in some sort of working way, I guess. Yeah, I wonder if it's also.
Yep.
Lucas just said that it's only for text files, or I'm looking for something like a text file, but it would be awesome if that would be also possible on any arbitrary object.
Yeah, another problem is that resolving the conflict always depends on what data do you have. So, if a text file, or it depends on how the data is presented. So I don't think there's a one-fits-all solution. Maybe just for plain text like this, but in this case, yeah, it could also be spend multiple columns and stuff like that. So it depends on the application. More questions?